Hi, my name is Leon Mira. I'm a software development lead at Unity's Accelerate Solutions group. I was technical lead of this project that we're presenting. I worked with Claire and a larger Unity team in close collaboration with Microsoft, and my role was mostly helping to put all the pieces together.
Hi, I'm Claire, and I'm a senior interaction designer at Unity in the Accelerate Solutions group. I had the pleasure of working with Leon and a great team at both Unity and Microsoft, and my role on this project covered design across UX, interaction design, and prototyping. This project was a partnership between Unity and Microsoft to create a dedicated mixed reality learning path on the MS Learn site, which was concerned with digital twins for industry. By utilizing an industrial use case partner who provided real-world wind farm data and business logic, we created a reusable digital twin template.
I would like to go now into a detailed overview of the project and its goals. We'll start with the personas. So we're targeting developers or tech champions. This would be somebody who's looking to get buy-in from somebody else at their business. The goals for them would be to learn what's involved in creating a mixed reality application for designing and operating a digital twin, and also to have a starting point for creating their own prototypes and projects. As a problem, we have that we're targeting a user not necessarily experienced in 3D development or digital twins or deploying to a HoloLens 2. So we're trying to teach these three things at once without being overwhelming to a user. The solution that we came up with is to create a learning path based on Unity and Microsoft technology, where you learn by doing in bite-sized modules. So it's a learning path where it's structured in pieces. You can start from the beginning and go all the way to the end, or you can start at different points throughout the path. If you don't need to go through each specific step, depending on your background. So in these modules, we base them on a realistic test case of a 3D wind farm. It uses a real-world location with live map data. There's live data from the IoT devices representing the wind turbines. In this case, they are simulated, but they could be real devices as well. You learn how to design your facility on your computer in Unity, and you learn how to operate it on HoloLens 2 in a mixed reality environment. You also, the knowledge lets you design your facility according to data-driven decisions, so you would be able to iterate on your design based on data coming in that you can adjust in your 3D scene, see what happens, and make adjustments as necessary. And then the last thing you learn is to operate and act in a mixed reality environment, how to operate and manage your set of turbines, leveraging digital twin technologies. So with the combination of the Azure technologies and the Unity visualization and user interaction, all running on the HoloLens connecting to the Azure backend, you're able to operate and then act on the input that you're getting from the data, get your insights from there, and then act accordingly. So the technology involved in this project is, well, this is published on Microsoft Learn. It's based on the Unity editor, runs on HoloLens 2. It connects to Azure Digital Twin and IoT Hub, and it takes in data from big maps and creates a 3D terrain out of it. The example also comes with 3D model of a turbine, and there's a few instances of it, so that you have a complete wind farm.
This wind farm use case is based on the concepts of design, operate, and act. In design, we built a Unity scene to help place wind turbines in a wind farm. And then in operate, we then connected them to operational data with the ability to monitor and observe telemetry data. So wind speed, ambient temperature, rotor RPM, power output, etc. And then in acts, a performance-related event occurs and an action can be taken. For example, a reduced power output due to icing, and then a ticket can be spawned to send a reset command. So to give a clearer idea of how this all manifested in the editor and on HoloLens, I'm going to play a short video so you can see. But I want to be conscious of compensating for any lag that people might experience, so I'm not going to full screen this. So to start off with here is a look into example of what this looks like inside the editor. This is a tooltip here, which is assigned to a turbine. This could be applied though to any element of a digital twin. And so as you can see, the naming is customizable, so a user could come back and build and adapt on this template as they need. If we continue on here, you'll see this shows the Big Maps SDK integration inside of Unity. And so on the top right is where you would input a developer key, and in the inspector below is where you can configure as necessary. You can see it gives the terrain area that we requested for the coordinates given. Another element then, as well as the tooltips, is what we call the site overview. Essentially, this is a list of all the turbines on the wind farm and the high-level summary of their status. So the detailed data view of a specific turbine then gives the data associated with it. So we should see that next here. This being the site overview, and yeah, here this being the detailed turbine tooltip. So for example, temperature, wind speed, and rotor speed. This again then is customizable, so both in the naming and the color values. So this would be deployed then to the HoloLens. We'll have you'll be able to bring in a turbine prefab object and place across the terrain in the editor. They can then deploy to HoloLens 2, which is the capture you see here. And then they can refine this design further, allowing you to move and rotate turbines while utilizing MRTK interaction components. Being mindful of giving the user control of the configuration of the 3D scene in their physical environment is important. So as you can see here, the triggering of the bounding box implies the ability to move and place the scene as you please. And then where a user may want to focus on a certain area or zoom out to view all of the wind farm in one view, the map manipulation gives them this power. So through both the map controls where a user can zoom, and also the far field interaction where the user can directly pan the map, move it around. So we included indicators shown there as blue arrows just on the side where the turbines are present but now out of view of the map. So if we go to the operate section here, the visualizing assets in an immersive setting sort of permits this user to experience the right data in the right context. So you can see here, I'll let this run and you can see in action the different interaction points where if you click on one of these turbines, it will then pull up the detailed overview tooltip panel. And inside of that, you'll see the temperature, motor speed, and rotor speed as well. So this is an event that occurs, as I said before, following a performance degradation on one turbine. So it's seen here by visual warnings cues that are across the site overview as well as the map. So you'll see here on the site overview panel as well. And the user can then see that the affected turbine, say, was out of view at the time, but you can see here by this indicator is also adapted then to the alert and reacts by adopting a status change in both color and scale. So if I let this run a little bit further, the user can then investigate the alert on the turbine tooltip, which gives them more detail around the data points and the status. So in this scenario, for an icing event, the user is given the option to send a reset command. This again could be customizable, but appropriate for our use case here.
I'd like to talk now about the structure of the Unity app. So these things you see here in the screenshot are the objects that we have in our scene. So this contains the local assets representing the digital twins. So our wind turbines, they are 3D models, which have been enhanced with some behavior for receiving and reacting to the data coming in from ADT. There's the objects that handle the connection to ADT. So you have to configure the object to be able to identify yourself to digital twin and be able to request data from it. There's the data visualization component. So, for example, the operate scene UI. where the data is displayed and buttons are available for the user to interact with. There's the terrain. So in this Big Maps operate object is where we consume the data from Big Maps, and through the Maps SDK that the Microsoft Garage created, we display a 3D map in the scene and we're able to interact with it. This brings us to user interaction, where through the Mixed Reality Toolkit and having the objects configured to receive that input from the user, we're able to manipulate the scene. So move the map around, select turbines, move the menus to where they need to be so they're not obstructing your view. So these are kind of the high-level components. Some of these, the ones with the little arrow here, have a deeper structure. So they have child objects that implement further functionality or split it across different objects. We'll see that in the inside the project, but at a high level, this is what we have. Next, I'd like to cover how we're driving the Unity app with ADT data. So the first point is how we're structuring the data for the app. We do that in Unity with scriptable objects. These are a special kind of object that you can use as data containers. So you can see an example here on the screenshot where there's the properties of a turbine. In this case, what's being shown here is the telemetry, so the data coming in very frequently from the turbines. You can also have metadata, which would be the kind of the more static properties describing the wind turbine. So in this scriptable object, we have information about the site as a whole, so the whole wind farm with its list of turbines, and then the detail about each turbine. The next part I want to talk about is how we're connecting to ADT. So the data that flows from the simulated devices through ADT, the way that data reaches our app is that it's exposed on the backend through the Azure SignalR service. So it takes a few steps from the simulator into the IoT hub, then through Azure Functions and Event Grids into Azure Digital Twin, the service. Next into SignalR, which is what pushes that data out, and we connect to it from the Unity app. So next, how we're receiving the data stream from ADT is by implementing the SignalR client inside the app. It's called negotiate, so we kind of tell the service that we are a client that wants to consume that data, and then we are able to start receiving it. In our example, we're sending it only every 5 seconds or so. This is of course adaptable. It could be many times a second, or you have to be careful with your usage, but it's adaptable to what you need. Then once that data stream is received, we need to share it across our app so that the UI can react to it, and whatever else needs to happen, the different components need to react to it. So we do that again through scriptable objects, but now we use them as events. So besides holding data, these objects can also trigger events, and at the same time send the data as a parameter. So that way we make it available to the rest of the app, and any other objects that are listening will get the data. So whether that's UI or loggers or maps, they just need to implement their listener to get that data, and that data will be available to them. Finally, after you get the data, look at it on the map, see the details of it in the UI, in our example, what we're doing is simulating an alert coming from a wind turbine. And then after looking at what you need, you can send that response back to ADT. In this case, we're doing that through the ADT REST API. There's a few ways, depending on what you want to represent, depending on the hardware you're simulating and the way you structure your backend. You could go through the IoT hub sometimes if it makes more sense. You can also, there's a way to connect directly to the Azure Digital Twins service, which is what we did in our example. So in our Unity app, we also have where we have logic to connect to the ADT REST API and update a property on the digital twin. One point I don't want to shy away from is why mixed reality and why our app on mixed reality. So I'll give you 5 seconds to look at the dialog on the right, say if it sounds familiar. 5. So yeah, now you might be thinking, this is not, you could have done this in VR, you could have done this in 3D on a flat screen. We could, but we're also proving the feasibility of all this, creating a path for extension. So for making this broader, more powerful. So we're providing a starting point where people can create their own projects from. They would have the key pieces in place, the different technologies working together. So this is just a sample, and possibilities are endless. So even with this example, if you look at a long-term vision, you could see how it could be extended to include, for example, on-site visualization. So you could be at the wind farm on the ground, looking at the sky, seeing the wind blowing around the turbines in color based on the speed, for example. So there's many things that are possible or could be possible in the future. You could incorporate weather data, other things that give you better context of the whole situation. One thing you could do, for example, is to implement the use case of being inside the turbine, so climbing up to the turbine, seeing the smaller components of it, and for example, monitoring speeds and temperatures, servicing, and that would be more a real life scale. So as a person, you'd see things that are not 80 meters tall like the turbine from below, but are components inside the turbine that are more like room sized. So it would be kind of inside a room, looking at control panels and smaller equipment, which would be very what you would be used to and would imagine normally as a mixed reality use case. There's of course remote collaboration and assistance that could be added. There's already tools provided by Microsoft on the HoloLens that take care of this. That could be integrated into the experience. And any other more human-friendly scale than a wind turbine that's 80 meters tall, the same principles could apply, and the same technology could serve that purpose. So could get you running your digital twin for any other application besides wind turbines.
So following on from Leon's points, I'd like to define the best interaction models that we had for our use case, as well as the spatial design considerations we took on board. So MRTK Unity is for anyone who doesn't know, is a Microsoft-driven project that provides a set of components and features used to accelerate cross-platform MR app development in Unity. We used MRTK to rapidly build immersive interactions, and it was invaluable. We had to reuse it from the ground up, and inside of that, then we set some interaction models that we leveraged to define a best practice approach. one of those being direct manipulation. So a bounding box with a proximity shader would be one example where it gives the users a better sense of the proximity when approached or when a contact is made with a button or, say, a turbine. It also suggests functionality itself. Another one would be pressable buttons or collidable fingertips. So this would be most apparent on the site overview panel, as well as perhaps on the tooltips, which would have closed components, or the site overview, which have a follow me button. Another would be affordance-based manipulation. So for those of you who don't know, it lets you manipulate the 3D object through a bounding box, along with the manipulation affordances around it. So we applied this to 3D turbine models in the design module, so then you could further refine and configure on HoloLens 2. And then if a user wanted to move, rotate, or scale, we would have a user's hand that if they were close to a 3D object, the bounding box and the nearest affordance are then revealed. So users could grab the bounding box to, say, move the whole turbine. Another model would be the far field interaction. So sort of essentially point and committing with hands. It was a new feature that uses the new articulated hand tracking system, and we were really excited to take advantage of it. Users could, in that sense, manipulate 3D objects from a distance. So it allowed for the control of the turbines and the UI panels at distance, whether that be reconfiguring the presentation of the scene to suit their needs, or scrolling through the site overview menu panel to quickly see the previews of the turbine tooltips. The transition then itself between near field interaction, far field interaction is really important. So we needed this to be seamless and interchangeable. Luckily, MRTK offers that. So for near manipulation, for example, when an object was within arm's length, roughly say 50 centimeters, the rays are then turned off automatically, encouraging near interaction. This project then uses a combination of near and far manipulation to interact with assets in the scene. So some assets lend themselves to one method, such as a collidable fingertip press of a button asset, while others benefit from the application of both near and far. For example, we used far manipulation to pick up a turbine using a directed ray, placing it in a distant point of the terrain, and then combine this with near manipulation, where the user can proceed to move closer to directly manipulate, say move or rotate the turbine using affordance-based manipulation. Another important area I'd like to cover would be the environment design, which covers a few different things, but so say for proximity and density of the environment, there's a lot of considerations there. So to take advantage of immersive experiences, we considered designing beyond the user's immediate view. So by allowing the user to configure the environment and the objects around them, they could adapt their experiences to their own physical space. So to extend this example, so you maybe consider the base or a tabletop of a digital twin experience, and how a user would integrate that into their current environment. So we thought a lot about that, and we went through several iterations at the beginning. In this use case, then, an imagery-based terrain forms the initial foundation of the wind farm. So you can see those in the images there. As the entire wind farm is of equal importance, then a circular form is taken to remove the notion of a focus in any one area, and encourages the user to navigate the terrain in mixed reality, to then investigate the wind farm from various angles, allowing them to walk entirely around it if they please. As an enhanced environment app, the terrain is then equipped with handles to place and adjust them on a suitable surface in a user's physical space, and allowing them then to change that surface if they want, or if needed. So we place the assets with realistic proximity then to features and other assets to permit operability. So particularly where moving parts are concerned, the density of the assets should be realistic. So initially we felt that the scene was too crowded, so we considered removing assets and calling on these at opportune times. So, for example, the tooltips only persisting one at a time to avoid visual clutter. There could be any number of turbines in the scene, and if you had all of those turbines at the same point, it would be an overwhelming amount of data, and so we were trying to curate that in some sense. Another solution which may suit a different situation would be expanding the scene to an appropriate overall scale. Another really important element would be the comfort. So as well as density, to ensure comfort for the user, the placement of objects must also be considered. So for areas of interest, the optimum placement for focus is about 2 meters from a user. So to ensure maximum comfort, it's critical for objects throughout the scene to reside, say 1.2 meters to 5 meter distance from the user. And we really tried to keep that as a good a template inside of this and project. We tried to keep best practice the whole time running through this, and knowing that this would be a reusable opportunity for digital twin creation.
One important topic I want to cover is integrating Microsoft and Unity. So when I say Microsoft here, I mean the tools for ADT and for communicating from ADT with the Unity app. So we run into some difficulties here. Unfortunately, there's no NuGet support in Unity, which would be ideal. So we had to find a way to generate the dependencies externally and then include them in our Unity app. I think one of the first things that we tried, just as a kind of as one of the steps in the research, I would say, was to create a console app using NuGet, getting all the dependencies figured out that way, and then putting them into our Unity app. And that's actually what we had to come back to in the end, because all the other options we tried didn't work. We actually also tried NuGet.exe. Didn't work for us. We tried a third-party NuGet manager for Unity, which looked very promising, but it also didn't work for us. So we went back to kind of the safer option, but it wasn't great because it wasn't very maintainable. So we would have liked it to be more kind of manifest driven, so that you could get new dependencies easier later. But we found no way. So one idea that we talked about and we kind of discussing with Microsoft is the possibility of extending this tool that they have, which is called the Mixed Reality Feature Tool, which already does a similar thing for getting the mixed reality dependencies into a Unity project. So one possibility would be to extend this to include Azure Digital Twin dependencies, to include SignalR and whatever else you might typically need in this type of app into that application, so that it's easy to update your Unity project to include them. This kind of sub point here, I don't think we talked about, but I just thought it would be cool if we end up doing that, to have some way of exposing that inside the Unity editor. And of course, the holy grail that I kept in gray here, because I don't want to give false hope, is official NuGet support in Unity. I know many people want it from both sides and from the community, and I hope it happens one day. That's it. It's just a wish for now. And then the other way we're integrating our Unity app with the rest of the tools in this pipeline is we're connecting to the ADT REST API. So in this case, we're using that to update a property on the digital twin. But there's, of course, a lot of functionality exposed there that we didn't need for our project, but it's available. One of the challenges we had was about modeling and visualizing data. So not that we had problems necessarily, but it was just challenging to take such a complex system and present it as simply as we could. So we had to make decisions on how much data to have in our example, from how many sources it came into our whole data pipeline, what we did with it at the end, on the other end of the pipeline. So we're only sending it to our client app through SignalR in real time. There's other things you can do for offline processing of the data. So in all that, we had to think about how to model the data. So there were different parts of it, like telemetry, which is the sensor data, kind of streaming continuously from the devices through the whole pipeline and into the app. There's the properties, which only change when something happens. So these are kind of more static data, like, for example, that describe the wind turbine, or statuses that only change when either there's a shutdown or a power on, or an event occurs. And then there's the events that could be alerts coming from the turbines, or even the events in the client app. So what does the app do when data comes in from ADT, or when a turbine is selected within the app, or when a user presses a button in the app. So there's a lot of components to think about here. The second part of this is who to talk to. So for some of these things, we could choose to go through the IoT Hub or directly to the Azure Digital Twin pipeline. So there's many ways to achieve some things, and you just have to find the best one for your situation. And then the next thing to think about is how the data flows inside the app. So once you receive that data, after it's gone through the whole backend pipeline, what do we do with it in the app? So we need to inform kind of all of our app that new data is available when it is. We need that to show up in different UI panels to highlight turbines that are selected or that are having a problem, and signal an alert, and even sending a command back to Azure Digital Twin. So luckily we're working in collaboration with Microsoft. We got great support for all this. But it is a complex system. So in our example, we abstracted a lot of the detail so that you can focus piece by piece. So starting kind of high level, only configure what you need to see it all working and understand how it is working, what the flow of the data is like, and then you can start digging in into each piece and start kind of discovering all that complexity as you go along.
So to build a little bit further on what Leon was discussing there, I'd like to talk about representing and visualizing data. So we used MRTK components in this use case. Turbine models were connected to ADT data streams that used MRTK tooltips. These are really useful objects that can be attached to assets in your scene that provide further data points. We attach tooltips to each turbine, and the data streams are then linked to that. In another environment, a user could choose to attach several tooltips to one object if it consisted of, say, many components that each needed their own data point. Another thing we utilized was scriptable objects. And if you don't know what they are, they're basically lightweight objects that can globally persist data across scenes and application runs. Each digital twin turbine prefab has a corresponding scriptable object in the Unity project that stores that data received from Microsoft Azure. So this digital twin application makes use of this scriptable object-based event system that then sends messages between the systems that do not have direct knowledge of each other, such as the Unity panels and the turbines in the scene. So then multiple events have been created as scriptable objects assets as well in the Unity project that can be referenced in the script to raise the event or be added to a prefab to listen for an event and react accordingly. For example, when a user selects a turbine asset in the scene, a defined event is raised. There may be multiple listeners in the scene that can react to this event, such as a turbine panel will react to the event to display operational information on the selected turbine. The map will react by focusing or essentially centering on a turbine's location. And then this turbine model will highlight to show that it's been selected. By using this event-driven scriptable object architecture, we created an integrated object-based experience essentially without needing to have each system, whether that's UI or 3D scene, to explicitly know about each other. We created a number of prefabs to accelerate the connectivity of your wind farm to Azure Digital Twin, and I hope by using them, by adapting them, and then also by understanding how they work, and that it is something that then could be utilized by someone going forward and create their own prefabs. Another thing was finding balance. So satellite imagery can provide contextual information to provide both realism and help to drive decision making. We leveraged Bing Maps for this. So in building the scene, we considered how much data we wanted to retrieve at each point. And there's always a balance between the data quantity and quality and performance. And it really is something that you need to test in device, and you need to actually have a user feel and what that comfort is about how usable any amount of data is at any one point. Not only how it's shown and visualized in the scene, but what actually is important at different points as well. There's also customization. So scene data can come from a variety of sources, ranging from CAD, or GIS, 3D content creation software, imagery, etc. In this wind farm use case, we created 2 Unity prefabs for this. So using Unity's prefab system allowed us to create, configure, and store a game object complete with all its components, property values, child game objects as a reusable asset, and the prefab asset acts as a template from which you can create new prefab instances in the scene. So when you want to reuse a game object configured in a particular way, in our case, it's the terrain or scenery in multiple places in your scene or across multiple scenes in your project, you should convert it to a prefab. So this is better than simply copying and pasting the game object, because the prefab system allows you to automatically keep all of those copies in sync. Any edits that we made to prefab asset were automatically reflected in the instances of that prefab, allowing us to easily make broad changes across the whole project without having to repeatedly make the same edit to every copy of the asset. And I think this is the kind of thing we try to include, so we could just really show the importance of creating this sort of standard, which will allow for better scalability, better adoption, and better maintenance of these kind of projects if you are building something out that was increasingly more complicated.
To summarize the technologies that we used, we classified them into mixed reality, digital twins, and supporting technologies. So in mixed reality, we have the Unity engine and editor, mixed reality toolkit, or MRTK, which handles a lot of the kind of abstracts away the complexity of handling the user input, user tracking within the 3D space. The version of MRTK that we used is based on the OpenXR standard. And we also use the mixed reality feature tool, which, like I mentioned, helps you putting the dependencies in place that you need to develop mixed reality apps in Unity. Next, for digital twins, we use the Azure Digital Twins service. We also connect to it through the ADT REST API. And we also have the Azure IoT Hub, which is what receives the data from the devices, in our case, simulated devices, and forwards the data onto the digital twin service, which is what kind of models the data as a digital twin. On supporting technologies, we have Maps SDK, which is built by Microsoft Garage, which takes in Big Maps data and converts it into a 3D object in our scene. We have Azure Functions and Event Grids, which help propagate the data through the backend pipeline, so from the IoT Hub into Digital Twin Service and then through SignalR. And we have SignalR itself, which is needs two parts. So one part of it is the Azure SignalR service, which runs on cloud, and the SignalR client, which we implemented in our app, which connects to the service to receive the stream of data. Now I want to share some thoughts about how to extend this to use it in any sort of industry or use case. So our wind farms example is just an example. The important thing is that if you focus on the key components, you can apply this to anything else. So in any digital twins scenario, you will need your IoT devices, and you can, for example, start with simulated ones and then change to real devices. You send that data to the IoT Hub, which captures it, forwards it on to the Azure Digital Twins, which gives it meaning and structure, so models the data and creates the digital representation of your facility. Then with SignalR, you get it out into your client Unity app, and that app handles the visualization and user input. So notice how I didn't mention turbines again, I think, or if I hadn't, it would have still made sense. So it can be, an airport, a space station, factory. It will all still apply. So use cases are universal, and the fundamentals are transferable. So if you use our example, dissect it, start with the high level, see how it's all working, and then dig into each component, you'll understand all that's involved in creating one of the systems, and you'll be able to apply it to anything else that's not a wind farm. And that's kind of the real more important value of this whole project. I'll touch on this slide very, very lightly because there's a lot of text. You'll be able to look at it in detail later. But the key thing that this slide wants to say is that the combination of technologies by Unity and Microsoft, in particular Azure, complement each other very well. There's a little bit of overlap, but each part of it has its very unique values that they bring. So in Unity, it's of course more about visualization, interaction, real-time kind of digestion into something simple and visual of that whole complex system. And Microsoft's side is more about availability, scalability, analysis. So this combination is very powerful. That's it for today. I want to thank Joe, Nick, Brent, Claire, everybody who joined us today, and everybody involved in the project. Till next time.